hypothesis spaces, roles of the learner, what the machine learners can do, hypothesis construction, a little bit more about the stats, and error measurement. Hopefully we'll have enough time to finish. I think we should be able to get through this section. Probably won't get to part 3.
Kevin, we do have to leave before night. You know.
Yes.
Okay.
Yes, this section's a little shorter.
I know.
No, I'm planning to wrap up by 8:45.
Okay, good.
So. All right. I still have my disclaimer. I'm still not a CPA. I'm still not a CFA. Okay. Boo! That's not good. All right. My graphics failed.
Reality isn't there.
Yeah.
There is no reality.
All right. We're in a reality-less world.
Out of sample.
That's one.
Okay. Let me see what happened. I think this was the, all right. So that was what was supposed to have been there. So this is the last 50 years of, or 60 years of the S&P 500. This is the percent difference of today's close versus yesterday's close. So these graphs look considerably different. This is just a waveform. Right? This is probably what you want to put into your machine learning. Right? Because these numbers are all within a tight bound. I normalize them. These are actually 0.05 to negative 0.05. I multiplied them by 100 for the graph, basically for humans. So those are within a tight range, and there are patterns in them. And the machine learning can actually find those. If I give it this as an input, what tends to happen in most machine learning is while you're in this range, it'll be able to make some kind of prediction. Maybe good, maybe bad, but as soon as you exit whatever range it was trained on, it goes out on. Right? So that's why we tend to want to use things like percentages. So this is basic data regularization. So let's examine some hypotheses on this data.
What did you say that the rifle was basic what?
Basic regularization. So you always want to regularize your input before you give it to a machine learning algorithm.
So could you explain more why you need one or the other one?
Sure. So machine learning is essentially about pattern recognition. Most of it is about pattern recognition. There's for the purpose of this discussion, it's about pattern recognition. So in and of itself, there's no pattern here, right? I, as a human, am already making lots of deeper inferences, right? So if I have a sufficiently sophisticated neural net to approximate a human brain, then yes, I can start making inferences about this. They may or may not be correct, right? Because once you start getting that complex, right, humans make mistakes, right? Which is why we resort to metrics. Right? We resort to, first thing I'm gonna do is a moving average of some frequency. And then I'm probably gonna add some Bollinger Bands, and I'm gonna add some RSI, and pick your favorite indicators. And I'm gonna look at those. I'm probably gonna do that for my machine learning algorithm, right? And we call that data regularization or feature engineering. So this is data regularization, where I'm just taking that data and directly translating it. So in this case, the waveform is simply representing this 5,000 as 5,000 divided by 49.75. Well, that's some number there. That allows me to say that that point and this point are the same, right? Even though visually they're quite different. But here, they're the same. And there's only a few outliers, but that's a major outlier. If I recall the actual time frame, this was the 89 crash. This, I think, was 08, or early 09. I think that's when that was. This isn't fancy. It came out of one of my programs, and I didn't bother adding all kinds of fancy axes and whatnot. So I just had n, which is my observation, but 0 was like 1950, and 16,929 was sometime last month when I pulled the data set. And basically I pulled the data set for this discussion. I don't trade I don't trade daily data like this. This
That's
is
the
not really.
1987 crash was the big long line there.
Okay.
That's
October
yeah.
1987.
You
Yeah,
exactly.
87, not
You put
89.
dates on those.
Yeah. I knew it was October.
If you looked at the prices on that day,
Yeah.
the prices were really wild. You had buy prices up here, then you had big spikes all the way down.
Yeah.
You had orders down here.
Yep.
Because the market makers weren't answering the phone. Anything larger than 200 was
Been
not
knocked
being
away.
answered. And if you were holding more than 200, you were getting screwed, I can tell you that.
I believe it.
Yeah.
I was fairly young, but I still remember that day. It was rough. Luckily, I was too young to have money in the market. But as you can see, there's only a few outliers that are that bad. Right? Most of the outliers, right? Just from a basic statistical standpoint, I can gather stats on this. I can see that most everything is within plus or minus 3%, and that covers almost the entire market.
I have a simple mind. The way I tend to just look at it is, if hypothetically I could pull the trend out and draw it as a flat line, these are the daily extreme or excursions from that normal midpoint.
Yes.
And it's no more complex than that in essence.
Yes, and that's one Markov chain hypothesis. And absolutely, that tends to be my basis of understanding of the market, and then all other understandings evolve from that. That just tends to be the way my mind works as well. Okay, so that was the reality that was supposed to be there. Let's see, there we go. All right, so then all right, I had a demo up. Okay, so let's take a few of those data points and try to do some curve fitting. So in this case, I'm going to be a human learner. And I'm going to make some hypotheses. And my universe of hypotheses are going to be expressed in this combo box. Why? Because it's a website that I could find. And it made for a good demo of what the learning process is like. So here I've got a set of roughly 20 hypotheses. Let's start looking at them. That doesn't represent that data very well. This is just the first 160 data points out of the data set we were looking at earlier. All right, let's try another hypothesis. Nope. Please enter a guess for C, all right? Not converged. Okay. So my input data was so crappy that it couldn't even give me a guess. All right, well, that must be a really bad hypothesis. All right, let's look at this one. Hey, there we go. Okay, at least it converged. It converged to something horrible, but it converged, right? So would everybody agree that this line is a really terrible representation of those red dots? Yeah. Right? It really sucks. And what we'll find out is all 20 of those hypotheses suck about this bad. They get a slightly better, not much. They suck. So as a human, this is what we do. So actually I would venture to say all of, minus the optimization, and even partly that one, of our prior discussions in the group have been a human learner going through just talking about the hypotheses that they have found that happen to work, right? But they've still been going through at human speed. They've put in a lot of hours, but we've probably still only examined out of the group maybe a couple thousand hypotheses and probably presented 30 of them. Right? So the whole point of machine learning is to do this only faster. So, what we want to do is we want to look at our reality, and we want to start constructing hypotheses. So one hypothesis might be that line, another might be the green plane, another might be the yellow plane, another gray plane. I actually want to send hundreds of millions or billions or trillions or more hypotheses through this space. And I want to just examine them. And I'm going to need, right, I want to try one, see how bad it is. Well, they're all going to be bad. The question is how bad. And I'm going to have to apply an algorithm for choosing a better one. And that's what the machine learning algorithms are about, is how do I choose the better one efficiently? Right? Because if I'm constructing an infinite number, right, if I'm selecting from an infinite space, right, then obviously I need infinite compute resources. So I have to come up with a better algorithm that will select in some way better. Hey.
It's reality, man.
I swear this stuff worked.
It's looking for the infinity plus one slide.
Okay, so see, I have a preview. All right, here's my cheat sheet slide. Here we go. All right, here's the cheat sheet. So, if you want to download it, you can go to fairlynerdy.com. They have lots of interesting cheat sheets. In particular, this one for hypothesis testing. So these are a few different statistical tests that you can perform. I'm going to say basically take your pick. I mean, look at the scenarios and the examples if you're doing your own machine learning. By the way, these slides will be available on the forum, so you can just download the slide presentation. And then when this slide doesn't copy into the open office presentation, you can email me and say, hey.
Quick question, Ken. Like each of these hypotheses, right? Like every one of those tests depend on the particular type of data sample, the underlying assumption of the data. So how do you correlate the particular test to the underlying assumption of the data set?
So, like this one, like these two are if a single population is equal to a target value. Everything assumes an unbiased sample. So everything assumes that you've taken a proper random sample. So that means that, for instance, if I were looking at babies born at this hospital, right? So my question here is, do babies born at this hospital weigh more than the city average? That means I have to have a random sample of all babies in the city to have an average.
So the question is, do they have to be normal distribution or some other
No.
distribution?
No, so they do not have to have a distribution. They do not have to be from a specific distribution. But they do have to be randomly sampled. That's the only measure that's required for all of these. So these will actually work for any distribution. Although some of your values will be very large for some of the oddball distributions. I would say that. Now, having said that, pretty much all instrument distributions that we're interested in are either going to be normal or log normal distributions. At least all the ones I've seen. Right? Like options model the entire stock market as a log normal distribution, for instance. And we have an entire market based around a zero-sum game of people betting against other opponents, and nobody has found a way that it's completely wrong. So it's a reasonable approximation of the actual movement of the stock market. So I tend not to worry too much about the perverse outliers, mostly because I restrict my worldview to trading instruments. Okay. So anyway, this cheat sheet, for those that really want to do the stats, Excel functions. You have Excel functions for almost all of these. So z-test, t-test, one-tailed and two-tailed basically is whether you just care about one direction or both directions of the curve. And if you're interested in more detail about hypothesis testing, I've got a book that's on Kindle Unlimited that I can recommend for you. It's actually a quick read, only takes
Sorry, and what?
Kindle Unlimited. Couple hour read, it's really not that long. So, scientific method. I promised that I would talk about how this stuff relates to the scientific method. Well, basically, it's a procedure that's characterized natural science, so that differs from what we are concerned with, right? Because we're not looking at natural science, but otherwise, systematic observation, measurement, experiment, formulation, testing, and modification of hypotheses, right? So we've got that iterative chain, right? There's really nothing completely unique about this idea. This is what all learning is. Right? But it works. So what do machine learners do? Well, if this is our learning process, this is what you and I would do as a human. That looks very similar. We have to come up with a constructor, though. So the machine learner has to be capable of constructing many, many hypotheses. Right? So I have to come up with some kind of formulation. Basically, that translates to code. Either you have to write it or you have to find it. Calculating error by some measure, we're normally going to use least squares error. We're going to talk about that in a minute. And then we're going to construct better hypotheses. So when people talk about machine learning, they tend to focus on this algorithm and constructing better hypotheses. This work, people have done this well. Probably better than you or I can. We could probably just reuse that stuff. This is where we as traders probably need to focus. Right? Is how do we construct our hypotheses? So one way is we just give it lots and lots of input variables. So one way could just be, and this is absolutely a valid way, sit down, make an Excel spreadsheet, as many columns as it will allow, and those are your variables. And then you just set machine learning on it and say, hey, which are the important ones? It'll give you an answer. And depending on how good the data was you put in those columns, that will be the determinant, much more than either the error measure or the hypothesis correction algorithm that you used. What you put in those columns will be the determinant of the validity of your answer. So that's the simplest Simon way. I tend to be focusing on ways that writing code, and I know many other people here will as well. So, who thinks this is a great way? Yes?
I got a question. You mentioned that many variables, right? But if you're throwing there different indicators or different open and close, I mean, all the variables that you can.
Yep.
So your output from the machine learning algorithm, what it would be? It would be a price? It will be a direction? I mean, the amount of variables that might be depending on the thing, but is the output itself. What is that, right?
So most machine learning algorithms go to one output variable. Some of them are based on classification, which would be direction, right, up or down. You could segment that into up a little, up a lot, relatively neutral, down a little, down a lot, or more shades of gray. That would all be classification. Then there's regression, which is about coming up with a value, like a prediction of it will go up 0.23758%. Probably you didn't come up with, the number of categories necessary to represent that. Regression is going to do it infinitely. There's different algorithms for both. I tend to favor classification algorithms, in part because that's what I care about. I want to know if I want to buy or sell. I don't really care about whether my exit price needs to be 83.5 83.2 or 83.2001. The difference between that, I'd much rather come up with a simple Simon than just get it wrong. Right, I think as Corey mentioned, or somebody mentioned in some prior presentation, right, pigs lose money. Right? When you try to eke out every last penny of your trade, you tend to lose money. So I just care about the categories. So pretty much every learning algorithm is based on one output. Neural nets can be based on multiples. That's because internally they have areas that are based on one. Ensemble learning, right, allows you to come up with multiple learners, each with one output, and then you come up with an overall algorithm that decides what to do. I tend to, at least for now, favor that overall algorithm is deterministic rather than machine learned, because I'm a little bit of a control freak, right, which I think most programmers are. Right? I don't know that all other disciplines are, or I won't say that any other discipline is, but I as a programmer have always been a little bit, I like control. So I like to know what that final step is saying. So I'd rather construct 50 machine learners, right? Each one predicting what's going to happen over, say, a different time horizon. Like I might have one learner who's entirely been trained on what will happen next 5 minutes, and another next 10, 15, hour, day. Even though I'm not going to trade day, I still want to know the direction. Right? And then I might have other ones that are trained to tell me about catastrophic events. And obviously I'm not going to trade if I detect a catastrophic event. Right? But I'm just going to make that a hard-coded rule. Do not trade if catastrophic event equals 1. Right? I don't need a machine learner to tell me that, nor do I even want one. So that tends to be what I do. Yes, it takes a lot of compute power to train all these different learners on all these different variables. And that's also why I've moved on. So I've moved away from things like NeuroShell simply because I don't have a programmatic API that allows me to construct the thousands of networks that I want to make. I have been considering talking to the guy and seeing what I can do about that. But for now, I haven't. For now, I'm doing stuff in Java.
That sounds interesting, but it's going to cost you over $10,000.
I already have NeuroShell.
You do?
Yeah.
You have all the modules that
I don't have.
Regularization has?
I don't have all of the modules. I have the.
Talk about MATLAB.
Or MATLAB, I'm sorry, MATLAB. Yeah, I meant MATLAB.
Oh no, I have NeuroShell, not
MATLAB.
MATLAB.
NeuroShell, right. MATLAB I was referring to.
Which also has modules, but I don't think it's 10,000 to buy all of the NeuroShell.
Yeah, it's a little over 10,000. I just priced it, happened to do it today, just for curiosity. I priced all the ones that Ernest Chin recommended that he liked, and it came to 10,000, a little over 10,350.
For MATLAB. NeuroShell, like I do have like the $3,500 version of NeuroShell, and there probably are another $3,000 worth of modules that I could get. The good part about NeuroShell, kind of like MATLAB, is it's very UI friendly, so it doesn't require the same level of programming expertise. Okay, so getting back to hypothesis construction. So I could do this, right? So getting back to our linear algebra, what does this mean? Right? So infinite dimension space of the real numbers. That is absolutely a valid hypothesis set. Unfortunately, because of that infinity, it's going to take an infinite amount of compute resources. So let's start simplifying. So let's look at D, where D is chosen by the algorithm and possibly by you. So there are various learning algorithms that will pick that. What you have to do, and most of these learning algorithms, what they do, you have to phrase your problem as a matrix. So you give it a matrix, and it will absolutely construct a matrix of this form, of R to the D. and then you multiply that matrix against your variables, say your stock indicators, and that makes the decisions. So you're probably going to have something larger than D and let the algorithm choose D. So you're probably going to have little d and big D. Where big D is all of the indicators that you would ever possibly care about. And whether you fully enumerate them in the form of the Excel spreadsheet that we talked about, or whether you write code that dynamically constructs them, doesn't make a whole lot of difference. It doesn't make any difference to the learning algorithm. It's going to choose a subset, little d. But you have to include in there something capable of describing truth. So your question earlier of why don't I just throw a bunch of data in a neural net? Well, my neural net, one of the common ways, and this was actually a mistake I made, was I failed to normalize my data. So I failed to normalize my input. I gave it raw values. So it didn't know what to do with, say, a change of 10. Right? Because my instrument could just incremented by 10. Well, the neural net was only capable of producing outputs between -1 and 1 due to the squashing function. It was incapable of ever producing the values that I needed. Sometimes they were +10, sometimes they were -10.
Why was it that? What was it? Because you did not normalize data?
At the time, it was one of my early mistakes, and I didn't realize I had to do that. I failed as I was going through the various steps of here's how to construct your rudimentary net. It was just one of those blunders that I looked at. I was like, why is my network never converging? It was never converging to an answer, right? And that's because my squashing function, right, always squashed outputs to -1 and 1. Now, it turns out that more recent neural net research has suggested other squashing functions that can produce values. Basically, well, actually, we can talk about that stuff if we have a session on neural net specifically. There are other squashing functions that allow more dynamic ranges. So it's just important that whatever you choose, you're capable of describing truth. So if you expect that whatever you're looking at, like Corey looks at VXX, trend following, right? You have to give it trend following indicators. If you're not going to give it any trend following indicators, it's not going to test a trend following hypothesis, right? So it can't find that truth. So your input has to include it. If the thing you're testing has mean reversion properties, you have to give it mean reversion inputs.
So is truth the thing you're trying to identify?
Yes, truth is what's actually going to happen. Now, it is actually unknowable, which is that's kind of the catch-22. What truth is unknowable. But we can make a reasonably intelligent guess about the boundaries where truth lies. Right? I don't have to know the truth is right there, but I do have to be able to say that it's here. Right? Whereas if I say that it's here,
So you're trying to narrow down the scope of truth.
or broadening. Broadening is fine. Making your hypothesis space broader only costs you more compute time.
Okay.
Rarely is it, well, okay. Depending on the particular algorithm, certain algorithms are more sensitive to noise than others. If you choose the right algorithm, giving it noise is okay. So giving it a broader scope rather than a narrower scope is better. Okay. So here we'll talk about what we don't see. So if you consider a bin with the red and green marbles, right, and the value of the probability of a red marble is unknown to us. It's not unknowable, but it is unknown. Right? And then if we pick n marbles independently, now this is actually independently with replacement, right? And the with replacement is important. Then I get a sample like this, where V is my fraction of red marbles received here. Okay? Now imagine if I don't actually get to see the bin. All I see is the sample. This is what you are doing in the stock universe, right? You are seeing these time-bound samples, where this is simply history, and that includes the infinite future. So you can't see it. But if your hypothesis that the future will in some way be based on the past. Now, if it isn't, there's no reason for any of us to be in this room. Technical trading is all bullshit, and we go home. Right? I assume that we all believe that there is information in the past about the future. Otherwise, we wouldn't be in the room. So, assuming that, then does V say anything about mu? Well, there's two schools of thought. One, no. The sample can be mostly green even when the bin is mostly red. Or, yes, V will be close to mu. And these two answers reflect the possible versus the probable. It is absolutely possible to get all red out of your sample regardless of what the bin contains. Right? The only bin that cannot produce all red is the bin that is all green. If there is one red, I can get a sample of all red because I'm using with replacement.
Oh, so it's replaced on each,
Yes, on each pole.
Each individual sample
Yes,
so it's not as a whole.
is based on the entire universe.
yes. Right? So that is literally the only one that makes that impossible. However, it becomes vanishingly improbable as my sample size becomes larger, because I'm making independent polls with replacement. And it's this probability that all machine learning is based on. So, can you guys tell me something unknown? Preferably about stock. Not a hard question.
Price tomorrow.
What?
Every answer is correct.
Give a specific item.
Google's price tomorrow.
That is absolutely unknown to me, and probably unknown to everyone here. Is it unknowable?
If we wait 24 hours.
I know a guy.
It is unknowable unless I wait 24 hours. So I would say that it is unknowable. Tell me something that's simply unknown, but is knowable.
Stock bucket. Well,
It's not gonna go to zero.
The what?
It's not gonna go to zero. What was your question?
Tell me something that is unknown, but knowable.
Options price and 1 second before expiry.
I would actually argue that that's unknowable, because that is directly dependent upon the price of the stock.
Are you driving at something that could be known, but we just don't know?
Yes.
i.e. the Amazon stock price exactly midday today.
Yes.
Which I don't think anything.
It is very knowable, but I don't know it. Right? So the thing that differentiates them is I have to make approximations. I have to come up with mental models.
Good evening. If you have items to check out or you need a library card, please
All right,
call the check-in.
I'll speed up.
If you are using our computers and
All right, so if we want to approximate the ideal,
save and you print your work,
right, this is what determines is learning
filling
feasible.
stations turn off automatically and close.
If I can approximate an ideal, then yes, learning is feasible, but only in a probabilistic sense. Right? There is always that vanishingly small probability that you are absolutely wrong. Everything you have studied in the past is wrong. So here's the formula. Here's an inequality that describes it, where epsilon is basically your confidence level, and 2e to the minus 2 epsilon squared times the number of independent samples is actually your bound. So I simplified that for everybody by constructing this table. So what this tells you is if I want to know within a 5% confidence, then I need, say, 500 samples to be right 84, what is that, 83.6% of the time. Right, so this is the amount of time I'll be wrong more than 5%. But with 1,250 samples, I'll be wrong by more than 5%, only 0.4% of the time. Right? But I have to have 1,250 independent samples. That's hard to come by. Right? It's hard to come by in our universe because there's so much correlation in the market. But if I can do it, here's your table. And this is a bound, by the way. This is actually a fairly loose bound because this is actually what's proven. So if I have this many observations, so this gives you the relationship between your observations and your confidence. So that's actually an important thing for stats. Unfortunately, we did not have time to get to part 3. This was the end of part 2. The only thing of part 3 that I will cover is like the first slide that talks about the forum. So there's a lot of stuff to cover in the technical trading universe. I would like to suggest that we all do it on a forum. And the whole reason that I do any of this and share anything is because I believe we're stronger as a community, right? So I want to see more ideas shared, and feel free to jump in, right? So people who contribute to the community are good. So we just started a forum here at javavisualizer.com/NWTTA. And when you first register, you'll see these top 6 or top 7, the general discussion, the languages for anybody who has questions, and then an area for active participants. I'm assuming that anybody who has done a presentation or has spoken up or given people ideas or whatnot, and with a little bit of participation in the forum, becomes an active participant. I just want to see people engaging and see conversation. It's great for us to sit back and learn, but it's much, much better. It's orders of magnitude better if we help each other. So I would like to encourage that. And that's where I plan to have all of, at least the stuff that I'm going to share, all the cool algorithms, testing methodologies, which would include more sophisticated flavors of correlation or error measurement, all those kinds of things, research papers, all that kind of stuff, and then various machine learning algorithms and other topics of that nature. Presentations are starting to be posted here. Right now, since it's my forum, I only have my presentation from October, and I'll have these shortly. Corey, if you would be so kind as to send some of your slides, and CJ, you did a presentation a while back as well. Caesar, you did one, and obviously, I think yours are already online, aren't they? Some, okay. We'll just get them all online. We also have been taking video, so I requested Suri take video because while not all of the machine learning topics they will not all build on each other. Basically, these first 3 are prerequisite to all the future ones because it's the very basic stats and other things necessary to understand machine learning. So anyway, sorry we didn't have time for all 3, but